In this tutorial, we will be continuing our discussion on Lewis dot structures, but this time we will be focusing on resonance structures. So we're going to look at NO2 again. We're going to keep going through the same pattern because it's really repeating on itself, and I want to make sure that we all understand this. So we have nitrogen, and we have two oxygens. We need to figure out what the valence electrons are for both. Here's nitrogen. Here's oxygen. 1, 2, 3, 4, 5, 6. There's 5 valence electrons for nitrogen, and there's 6 valence electrons for oxygen. Add those together. That comes out to be 17. Notice that there's a negative sign up here. When it's negative, you add electrons. So it's -1, so we're going to add 1 electron for a total of 18 electrons for this structure. Now we're going to arrange the atoms where the most electropositive, or in other words, the least electronegative atom is the central atom if one exists. So here's nitrogen, here's oxygen. Nitrogen is the furthest away from fluorine, so it's going to go in the middle. And there's going to be oxygens on either side. Alright, so let's write that again. We're going to start putting things together now. We have 18 electrons total. Draw a single bond between the atoms, so from the atom into the center. And now subtract those single bonds from the total valence count. Remember, each single bond is equal to 2 electrons. So we have 2 bonds, so that's a total of 4 electrons. 2 times 2. Going to subtract that out to be 14 electrons. Place pairs of electrons around the peripheral atoms until the octet is reached. So we have 2 electrons here. To get up to 8, we need 6 more. 4, 5, 6. We have 2 here. We need 6 more. 1, 2, 3, 4, 5, 6. So there's our 8. There's our 2 octets. 2, 4, 6, 8, 10, 12 total. We have 2 electrons left in this set. So let's redraw this. Well, we start off with 18. Let's go back to this. Sorry. Those are from the bonds. Those are from the lone pairs around the oxygen. If any valence electrons are left, place those electrons around the central atom until the octet is reached. So 2, 4, we have 2 more electrons, and that makes 8. So that makes 6. 2 from each bond, and then a lone pair. Alright, so now we have to check for the octet around each atom. We know the oxygens have octets because we just counted them as we were adding them in. But the center atom has 2, 4, 6. We need 2 more electrons. So let's redraw this, and we'll look at our rules again. I'm not going to worry about the valence electrons count because we already have all our valence electrons accounted for. If the octet is still not reached, then multiple bonds must be used. Take a pair of electrons from each peripheral atom to form multiple bonds, and octet is satisfied for all atoms. Alright, so we're going to take one of these pair of lone pairs and make a double bond out of it. Now our octet is reached on the nitrogen. 2, 4, 6, 8. Let's check for the octet for all of them. 2, 4, each one of these is worth 2, so that's 6, 8. 2, 4, 6, 8. Alright, so I want to talk for a second about the fact that I use the oxygen on the left to form that double bond. I could have just as easily used the oxygen from the right and had that be the double bond. This is what's called resonance, because it could be either way. O3 is another example. Resonance structures are equivalent structures. The true electronic structure is a hybrid of the two. So notice here's O3, which is actually ozone that we have in the atmosphere. We have 3 oxygens. We have a double bond on the left-hand side when they did the Lewis dot structure. And on the right-hand side, they also have a double bond, and it flips back and forth. The true structure is a hybrid. So instead of having one time on the left and one time on the right, they blend them together. And notice that there's a dash. So the real bond is actually 1.5, not 2 and 1. And that's a resonance hybrid structure. So if we go back up here, this is a resonance structure, and it's signified with a box around the structures. So that way somebody reading it knows that it can go in either direction. The true hybrid is what we had. It's blending the two together, where this is more of a dashed line, and you have 1.5. This is the true value. However, up here is the resonance form. Alright, so let's try this again. CO3 with a -2 charge. We have carbon and oxygen, which are here and here. We need to figure out the valence electrons. 1, 2, 3, 4, 5, 6. According to our equation, we have 1 carbon, and it has a valence number of 4. We have 3 oxygens with a valence number of 6. Let's go ahead and add those up. Notice we have a -2 charge. That means we're going to add 2 electrons. If it was positive, we would subtract. So we have a total of 24 electrons here. Now, let's compare the two atoms. Carbon is further away from fluorine, so we're going to do that one first. That's going to be in our center. And then the oxygens are going to be around it. That's our center atom. Now let's connect our peripheral atoms to our central. So we have 2, 4, 6 electrons used here. That comes down to 18 electrons left. From here, I need to fill in my lone pairs. 4, 2, 4, 6, 2, 4, 6, 2, 4, 6. That adds up to 18. So we've used all our electrons at this point. We have no more to spare. But if we look at our octets, our oxygen has the full octet. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Our carbon only has 6, 2, 4, 6. We need another couple electrons here, but we don't have any more valence electrons to give up. So we're going to take some of these lone pairs and make a double bond. However, I did not necessarily have to make it here. I could have made it at the bottom or to the left. So we're going to make a resonance structure. And I don't have a whole lot of room, so you'll have to bear with me. Instead of making it on the right, I'm going to make it at the bottom this time. So instead of having 6 electrons around here, I'm only going to have 4 for that octet. And then I have one more set. I'm going to go on the other side. Maybe I'll have enough room over here. Barely. Alright, on the left, I'm going to have the double bond. Fill in the lone pairs. Okay, you will see now that I have 3 different structures, I'm going to put a square box around them to signify that those 3 structures are indeed in resonance. We're going to have one more example. So, SO2, sulfur dioxide. We have S and O. They're here and here. They're in the same row actually. 1, 2, 3, 4, 5, 6. So 1 times 6 is 6. 2 times 6 is 12. So we have a total of 18 electrons. So sulfur because it's further away from fluorine, it's going to be the atom in the middle. Connect the peripheral to the middle. So we have 4 electrons used right now. That gives me 14 left to deal with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 used up on the oxygens. I need 2 more, so I'm going to put them on the sulfur. Now let's check for octets. Oxygen's an octet. Oxygen's an octet. Sulfur only has 6. 2, 4, 6. We need 2 more, so we're going to steal a couple electrons from the oxygen on the right. I could have, however, stolen them from the left. So let's go through that again. And I could have that double bond on the left. It doesn't matter because it's in resonance. I have to actually tell people that it's in resonance though. So whenever you have a resonance structure, make sure you actually signify that by drawing both structures, or all 3 structures, however many there are, with a double arrow saying it's going back and forth, and a box around them. And that's how you do resonance.